your paper now, the Dragon Hatchling paper that's out, it is described as the missing link between the transformer and models of the brain. So how does this paper blend together what we've been talking about so far and form a missing link?
We introduce a post-transformer architecture. It's an architecture which relies on attention and which fundamentally has properties of a massively parallel system of neurons. So you can look at it as a system, a network of a large number of neurons, which also communicate with each other. They are artificial neurons, but they do have some of the properties of natural neurons, especially in what pertains to how they address the problem of attention. And in some sense, this architecture is the missing link in the sense that it is more biologically plausible, it is closer to the brain, and it also hopefully, this is something to be verified in experiments, but hopefully explains some of the mechanisms of the functioning of reasoning in the brain, or at the very least provides a plausible explanation of how the brain could use certain mechanisms to achieve performance known from machine learning models like the transformer. So this is the connection to the brain, and the connection to the transformer is such that we rely on an attention mechanism which is at a very general level the same. It is implemented in a different way. There are a couple of elements which we may dive into, which are technical. It is what is known as a state space model. State space models are a form of reconciliation of some of the concepts of recurrent neural networks and the transformer. The fact that it is a state space model means that attention does not have to be viewed like a lookup structure. You can also view it in this local perspective of actually paying attention to certain concepts. You don't have to look at it as looking back in time. So you have the state space interpretation.
Excellent. All right. So with this kind of state space interpretation and this Dragon Hatchling architecture that you have that could potentially replace a transformer, it sounds like it's exciting, not only because it could be a more efficient replacement for the transformer and could be something that some years from now is kind of the go-to thing when we build a large language model. Instead of going to the transformer as your choice, you go to some animal from the baby dragon family. And so that seems like one part of it that's really exciting. And then the other part you mentioned there is that it could end up being that this could help us understand the way that learning happens in biological systems better. And so it could potentially not only be a machine learning breakthrough, but a neuroscience one as well.
That's exactly the hope, and that's why we're approaching it. There's one more aspect which is perhaps worth mentioning, which is that it's kind of pointless replacing the transformer in places where the transformer performs well. But there are places where the transformer does have its limitations, and the human brain is able to overcome them. These pertain to lifelong learning, to reasoning over long periods of time, learning with experience. So these are areas where a human mind can spend years potentially diving into a subject to perfect the state of the art and to push the state of the art forward. This does not have to be scientific state of the art. It can concern any kind of work activity, any specialized task in which the human mind is able to do it, whereas the transformer has its limitations. There's a lot of ongoing discussion about specifically reasoning models, synthetic reasoning models today, whether they are able to extend reasoning beyond patterns that they have seen in their training data, whether they are able to generalize reasoning to more complex reasoning patterns and longer reasoning patterns. The evidence is largely inconclusive, with the general no as the answer. Currently, machines don't generalize reasoning as humans do, and this is the big challenge where we believe architectures that we're proposing may make a real difference.
Fantastic. So the idea is that the baby dragon family, starting with the baby dragon hatchling, BDH, we could have a model that has no limits on its context window, it sounds like. So you could theoretically have, as much learning as you want and be able to attend efficiently over all of that information.
That's true. And the answer is yes. One thing to always bear in mind is that there's no such thing as a free lunch, in the sense that if especially for those of the audience who are familiar with post-transformer architectures which have appeared in the past, there's often this attempt to somehow make context infinite, but at the same time compress it. Just have a kind of a memory the size of a peanut and hope for it to be able to somehow compress long reasoning chains of thought or long sequences of text. In our case, the way the architecture is designed, and obviously we invite everyone to have a look at a paper and take a look into the details. But the idea is really that there's so much space, so much flexibility in manipulating, storing context, that this is not a bottleneck, and at the same time it's efficient. Here, for the sake of analogy, if you take again the human brain, one parameter that I mentioned at the beginning is the scale of it. It's 80-100 billion neurons, but also if you look at the way the brain represents its state, here we're talking about synapses. There are like 100 trillion of them. Not clear exactly how many, but it's 100 trillion. And I can assure you that none of us process 100 trillion tokens in a lifetime. It's orders and orders of magnitude less. So we're talking about a system which does have the storage space. It does have the state in sufficient quantity to be able to process long context, but needs to do so efficiently, so as not to waste time on doing some operations which don't move it forward.